Alright, in this video we're going to go over Unit 8 worksheet, which has to do with lipids. And number 1 says to predict the products of the saponification reaction that occurs when the following fatty acid reacts with NaOH. We did something similar to this in lab, and that's where we learned about saponification. So I'm going to go over how we would find the product. So it's this fatty acid here. We know this is a fatty acid because it has a long fatty tail, and the carboxylic acid. And when this reacts with sodium hydroxide, it produces a carboxylate salt. Carboxylate salt. We've talked about the carboxylate ion. That's where the H is removed and it's just COO minus. This is COO minus with Na plus. So let's look at what that would be. I'm going to leave it in the condensed form here to make it easier to write. And nothing happens to the fatty acid tail. It remains exactly as it was. The only thing that reacts here is the carboxylic acid and then this NaOH. So all of this stays the same. And I'm going to draw this out in this fashion. Here's the carboxylate ion, okay? And then the Na will sort of combine with this carboxylate ion and it will form soap. This would be a solid. So this would be something that would not be soluble in water if it has solidified. So it would be just kind of solid soap that would float to the top like you saw in lab. Now a small amount of it might be soluble in water, but most of it would be what we call salted out. So in addition to this, in the actual process of making soap, we would add excess Na. We would add, and we did this in lab, we add sodium chloride in excess in order to salt out this ion. So to get it away from the water and get it to combine with sodium to form a solid carboxylate salt. And then the other product is just water. Okay, so this OH here will combine with an H there and they'll make water. Okay, so that is it for saponification. Remember that the product of saponification is always going to be a carboxylate salt. So your product should always be a COO minus and some ion here, whether it's sodium or magnesium or something else. The next part of this question asks, are any of the molecules above amphipathic? Yes, this is amphipathic. And we know that because it has a very polar end. This carboxylate ion is very polar, and it has this long nonpolar tail. So that makes it amphipathic. Okay, the next question says, arrange the following molecules in terms of increasing melting point, lowest to highest. So I'm just going to rate these from 1 to 4. And I'm going to start by looking at the structures of these. I know that these two are unsaturated, and I know that unsaturated fatty acids have a lower melting point than saturated fatty acids. And these are unsaturated because they have double bonds. In this case, each one has only one double bond. These have no double bonds, so they are fully saturated. And we learned a long time ago in class that the larger a molecule is, the more strong its London forces will be. So if we just compare these two fatty acids here, what we see is that this one is larger. It has more carbons in it, 16 total. This one only has 14. So since this is saturated and it's the largest, it is going to have the highest melting point. This one is saturated and has 2 less carbons, so it will have the second highest melting point. Now if we look up here, compare the number of carbons here, we have 1 plus 8, that's 9, 10, 11, 12, 13, 14. So these also both have 14 carbons. So we can make the direct comparison between A, B, and C because they all have 14 carbons. But since these are unsaturated, they will have a lower melting point than fatty acid C. All right, so now we need to look at the difference between these two. Cis fatty acids, if you remember, are going to have that kink. They're going to have a bend in the structure, whereas trans fatty acids are going to be more flat. And if they're more flat, they can stack on one another and have stronger interactions than if they're bent. So, as a result, the trans fatty acid will have a higher melting point than the cis fatty acid. It's going to take more energy to break up the interactions when these stack on top of each other than it will to break up the interactions between a more disordered structure that would occur with a bunch of molecules that are bent. All right, next question asks, draw the product when this fatty acid has been fully hydrogenated. If it's been fully hydrogenated, that means it turns into a saturated fat or saturated fatty acid. And basically all that means is that we get rid of all the double bonds. There's 1, 2, 3 double bonds in this structure, so we just get rid of them all. I'm going to count the carbons. Well, actually I'll just write these out in order. So CH3, CH2, this becomes a CH2 because it's been fully hydrogenated. So this double bond goes away, replacing that with 2 CH2s. Then the next CH2 here. Then we come to another double bond. Again, these both become CH2s because that double bond goes away. The next double bond here and here both become CH2s, and then we're followed up by 1, 2, 3, 4 CH2s, and then the carboxylic acid. Obviously, we could have written this in a more shorthand form to make it easier, but I wanted to show you how each individual one has been fully hydrogenated, and we're just left with a saturated fatty acid. The next part of the question says, do the same, but now for partial hydrogenation, you may choose how many double bonds to keep. Partial hydrogenation means that we limit the amount of hydrogen that we're adding to the reaction. And so only some of these double bonds are going to get hydrogenated. So I will just leave one double bond in the structure, and I'll say that we added enough hydrogen to hydrogenate 2 of the 3. So the rest of these here, 1, 2, 3, 4, 5, 6, 7, 8 CH2s remain. Okay, so at this point I'm here, so I'm going to write out the remaining 7 CH2s. And then the acid. Okay, that needs to be in there as well. All right, and you could have drawn this out with just 1 double bond hydrogenated. You could have left 2 double bonds in there, but it would be wrong to leave all 3 double bonds in there. And it would also be wrong to leave no double bonds in there because it was only partially hydrogenated. All right, I hope that was helpful. I plan on uploading another video for some additional organic reactions, so look out for that.